All right, lesson 6 talks about inverse functions. I'm hoping that at some point in your math career up until this point, you actually have seen inverse functions or relations, but if not, that's all right. A couple definitions we should go over before we move on is that there's a hierarchy of things we can put on a graph. Essentially, if we put a drawing on a graph, we call it a relation. If it passes the vertical line test, we call it a function. And if it passes the vertical line test and the horizontal line test, then we call it a one-to-one function. Okay, so essentially here, what we're saying is if these are all of our x values and these are all of our y values, then any x creating any y we call a relation. Okay, and when we have one x producing only one y, then we call it a function. Now, another x can produce the same y. However, if one x produces one y at any given point, that is a function. It's okay if a different x produces the same one, but what we can't have is something like 1 producing 1 and 2. So from every x, we can only create one y. The y's don't have to be unique, but they do have to be singular. That's what we call a function. And then a one-to-one function is where the y values are unique. And I'm just making up these numbers. Doesn't really mean anything. But a one-to-one, and actually my mathematician who doesn't like to write, I'm just going to use numbers here. A one-to-one is where each x value produces a unique y value. So there can't be any repeats. Okay, so relation is pretty much anything that is related to each other. Function is where one x value produces one y value, but a different x value can produce the same one. And you can kind of see that with like an x squared, right? -1 and +1 both give us that y is 1, but it's 1 each. And then in a one-to-one function, each unique x value gives us a unique y value. And we use the vertical line test and the horizontal line test. Some of you have mentioned to me use this, it's called the squeegee method that somebody has taught you to say. Either way is fine. Okay, with a vertical line test, again, this mathematician does not like to write out words. We're going to call it the VLT and the HLT, horizontal and vertical line test. One thing to note, this IFF is again a mathematical shorthand for saying if and only if. So that means we're talking about a very strict restriction. Okay, so examples. We just talked about the parabola. Here is a parabola. A vertical line test means at any point I'm going to draw a vertical line. I'm going to scan my graph, and if my pink line intersects the graph only at one point, no matter where I draw it, then this is a function. It has passed the vertical line test. Each x value only has one y value. Alternatively, if I have a graph that looks like this, and I draw my vertical line test, it passes. But I can also draw a horizontal line test, and it passes. The green lines cross at only one single point, and the pink lines cross only at one single point. So there's only one place where the green lines touch the graph, and there's only one place where the pink lines touch the graph. So this is what we call a one-to-one function. So it has to pass both. It can't just be one or the other. If it passes the vertical, it's a function. If it passes vertical and horizontal, then it is one-to-one. Graphing a relation and its inverse. So I've seen many different ways of explaining this. And one of the ways, we're going to talk about this visually, and we're going to talk about this algebraically. And the best way that we can think of this visually is an inverse relationship is a reflection over the y equals x line. So remember we talked about a flip backwards or upside down as we flip it over the x or y axis. When we talk about an inverse relationship, we are flipping it over y equals x. Means 1, 1, 2, 2, 3, 3, and so on. So here is our line, and we are folding it on the diagonal. Okay, it's as if we're making two triangle sandwiches. I'm folding it over on the diagonal. Now, this function is an absolute value function that has been shifted to the right 4 spaces. So 1, 2, 3. My vertex is here. Okay. This is my pink function. Essentially, what I want to do is I want to fold this graph along the black line that I've drawn, and this is going to, excuse me, cause a reflection. Where would the reflection be? I'm going to draw the reflection in green. If I take the top part here and flip it over to the other side, it's going to end up like this. Okay, so I'm flipping that over to the black, flipping it over the black line. If I take this part and flip it over the black line, then my intersection, my vertex at 3, 0 is now going to be at 0, 3. I want to connect this line here, and it's going to go out this way now. So we've kind of turned it over on its side. We've taken the pink graph, folded it over the black line. It's now on its side, and you can see that the key points of the vertex, which used to be at 3, 0, are now at 0, 3. And that's actually exactly what we want. We are exchanging the y for the x and the x for the y, and that's the inverse. Another way to depict the inverse is by writing a little -1 in the function, and this is saying that we're drawing it backwards. The inverse of this. Some examples I've seen is where they switch places, the x and y switch places, and then you just have to resolve for y, but essentially you're doing the same thing. As long as you can kind of understand mentally, visually what we're doing, we are folding our graph in half along the diagonal of the black line. 1, 1, 2, 2, 3, 3, 0, 0, etc., etc. You are swapping. I guess I should have written this in the appropriate colors. My original vertex was 3, 0, and I'm exchanging the positions of the coordinates. 0, 3 is where my new vertex is. And also, your graph is now sideways in this case. Okay, it is possible that you might need to restrict the domain when we do an inverse. We can do this algebraically, means we can solve it using mathematics. So first, let's graph this function as is. That is a quadratic, and we have shifted it up 2. So my vertex is at 0, 2. And then we have, oops, this one should be a little bit higher. There we go. Okay, here is my parabola. The domain here is all reals. my range is that y has to be greater or equal to 2. Now, when I solve for the inverse, now I want to do the inverse function. I want to reflect it over the x equals y line. And if I do this visually, all I need is some key points. So let's take a look at what this point is. This point is 2, positive 6. And this is negative 2, positive 6. To reflect this over the diagonal, I could just swap all the points, swap these guys. So instead of 0, 2, it's now going to be 2, 0, my vertex. Instead of negative 2, 6, I'm going to have 6, negative 2, and 6, positive 2. Here is my reflected parabola. I can do this graphically. However, let's not forget that in order to flip something sideways, what we are doing is we are calculating the inverse. Means instead of having a y function, y equals function, we want it to be an x equals function. So now I am going to solve for x, means rearrange the equation into x equals form. So this is going to be y minus 2 equals x squared, or y minus 2 square rooted equals x. And this is where we have a domain restriction. We need to have y minus 2 be greater than or equal to 0. So that means y needs to be greater than or equal to 2 in order for this to mathematically make sense. So this is a square root function shifted to the right 2 points. So square root function normally looks like 0, 0, 1, 1, 4, 2, like this. If I shift it over to the right 2 spots, I'd end up like this. Let's see, 1, 2, 3, 4. And guess what? This pink function is this pink function. But we have restricted the domain because we know that we cannot take a square root of a negative number. Okay, now I have seen some tutorials on video on YouTube, sorry, where they say, oh, you know what? Take y squared equals x squared plus 2, and then just rewrite it as x equals y squared plus 2, and then solve for y. Make it into y equals again. And that's not technically wrong. However, I find students confuse. You're going to end up with exactly the same thing. I find when students do it this way that they confuse the original equation with the inverse equation, and they then when the question asks like further comprehension questions about the inverse versus the original and stuff, they can't remember the difference between the two because we are going to get into more complex equations. So I like to leave it in this way. The original equation is in y equals form, and then I write the inverse equation in x equals form, knowing that I have transformed. I'm graphing it as if it were a y equals. Okay, so solve it like this, and then if you want to rewrite it in y equals form, just make sure that you are telling yourself this is, maybe write a subscript, y sub I, so you know that this is the inverse, rather than getting them confused. But either way is fine. Essentially, an inverse function is what happens when you solve for x instead of y, and visually, it is folding our graph on the diagonal of the y equals x line and essentially flipping the graph or reflecting the graph over that line. Okay. That is my example. There's an extra graph here, which we don't need. Let's take a look at some more algebraic examples. Okay, this is the function f of x equals 5x minus 1. How would I write the inverse? So I'm going to write this like this. Y equals 5x minus 1. I want to rearrange this into x equals form. So that means y plus 1 equals 5x, or y plus 1 over 5 equals x. So my inverse function is x over 5 plus 1 over 5. This is the inverse. Once you have x isolated, that's your inverse function. Okay, and it can get as complex or as easy as you like it. It just depends on your algebra skills. All right, here we have y equals negative x over 2 plus 7. What would be my inverse function here? Okay, I'm going to have to multiply everything by 2, negative 2, to get rid of that fraction. And I need to add 7 to the y. So, okay, let's do this step by step so you can see what I'm thinking here. This is what I am thinking about. This would get me x isolated. So when I write it in inverse form, I'm actually just going to distribute this here. This is going to be negative 2x, right? Because we're technically graphing a function of x, plus 14. So I isolate for x and then I write it in inverse form. All right, same thing here. Y equals x squared plus 8. So this is going to be y minus 8 equals x squared. So I need to square root both sides. So this is my inverse function is the square root of x minus 8. So hopefully you can see this is not really complicated. You just need to pay attention to your BEDMAS rules, right? And your solving equation rules. So if y equals x plus 1 all squared, then square root of y is x plus 1. Square root of y minus 1 equals x. So the inverse function is the square root of x shifted down 1. Does that make sense? This is a quadratic shifted to the left 1. Right? So when we reflect it, the x-intercepts become the y-intercepts and vice versa. All right, let's do one more here. Y equals square root x minus 6 plus 3. Solve for x. Y minus 3 equals the square root of x minus 6. So y minus 3 all squared equals x minus 6, which I'm just going to add to the other side. So there we go. My inverse function here is going to be x minus 3 squared plus 6. Right? So here, instead of being shifted right and then up, I am shifting, oh, yes, shifting right 3 up 6 rather than shifting right 6 and up 3. I'm inverting the transformations that I'm doing. Okay, last couple here. Y equals x plus 2 cubed plus 8. So y minus 8, and I'm just going to do a few steps in one. This is going to be a cube root plus 2 equals x. All right, if I did that too quick, I minus the 8. I cube rooted to get rid of the cube there, and then I, oops, should be minus 2, minus the 2 to get the x by itself. If you're not sure how I did that all in one step, try doing it step by step and invert one piece at a time. So this is the cube root of x minus 8 minus 2. And the last one, oh, this one is yucky. Y equals 2x over x plus 3. I have x's in 2 spots here. This is going to be gross. Let's try. Y times x plus 3 equals 2x. I'm going to distribute this. Yx plus 3 equals 2x. Let's bring everything to the same side. Yx minus 2x plus 3 equals 0. Okay. X here, let's factor it. X bracket y minus 2 equals, I'm going to move the 3 to the other side there, negative 3. So x equals negative 3 over y minus 2. All right, this one was trickier, but still doable. The inverse function of this rational is negative 3 over x minus 2. Okay. So algebraically, we are solving for x, and our final answer is written as an inverse. Of course, we always use x when we are graphing, so we do want to make sure that we are writing our final equation with the x in here. But visually speaking, I find it much easier to do it this way. If your brain did not like this and you prefer to just start off with x equals 2y over y plus 3, so you want to take the original equation and just swap the places of the x and y's and then solve for y, you're going to end up with exactly the same answer. So if your brain likes this way better, do it that way. That's fine. My brain appreciates this way better, but it's up to you. At the end of the day, if this is your final answer, you did it correctly. All right, and in our last page here, it just gives you two examples to look over, visualizing what we're doing. So the original graph is given here by the solid line, right? I'm going to draw in the y equals x line in green. We are folding it over in half. I can see the vertex of my pink to be at 0, -2. So when I go to graph it in black, I know the vertex will now be -2, 0. And you can pick any point on this pink line and just swap the x and y values. Let's do this one. This is 5, 1, 2, 3. So that means when I flip it, it's going to be 5, +3. So actually ends up being in the same spot. Oops. Nope. My apologies. 3, 5. 1, 2, 3. 1, 2, 3, 4, 5. There it is. Not a little mini brain fart there. Okay, and let's take a look at this point here. For example, this is -5, +2. So that means on the black line, this would be +2, 1, 2, -5, 1, 2, 3, 4. There it is, 5. So I took 1, 2, these 3 points, and I have graphed them 1, 2, 3 right there. And you can see that the V is sideways, folded over the green line. Okay. Last one. This is our smiley face from one of our previous examples. Here are the eyes. 5, 5, -1, 5. I believe this was -3, 2. Bottom of the lip was 2, -1. Top of the lip, let's see, that's a 5. So this is 7, 2. So when I flip it, again, I'm flipping it across the y equals x line. Let's start with the eyes. 5, -1, 5, -1. That's the first eye. And 5, 5 doesn't end up changing because it's actually right on the line. So that's our invariant point. So this is 5, 5. This is 5, negative 1. And then for the smile, 2, negative 3, 1, 2, 3. So this is 2, negative 3. Middle of the smile is at 2, negative 1. So now I'm going negative 1 up 2. Oops. I'm not sure how I'm drawing these hearts, but it is cute, even though it is a bit distracting. So negative 1, positive 2. That's the bottom of the lip. And then 2, 7. So there is my smile. I have flipped it over. So when we do an inverse, the invariant points are the points x, y, where y equals x. So in this case, 5, 5, or 0, 0, or 1, 1, and so on. And that brings us to the end of this lesson, I believe. Your homework is to try some of these questions from the textbook PDF, or you can try some of the Delta Math questions. The goal for me is if you are able to solve algebraically, can you invert an equation or a function, and can you visually invert an equation or a function? And again, all we're doing here is taking key points and we are swapping the positions of the x and y. All right, that is the end. Enjoy.